RASIG. I haven't attended one in the last few years since I retired, but I am very pleased to see it continuing with the active group and continuing the various awards. The title of this, which I came up with a couple of months ago, talks about the role of PMAKE analysis. And the interesting thing is 50 years ago, in late April, I was working on my master's thesis at MIT, which had the title Unreliability in Rail Freight Operations. And I was so successful in that thesis that 50 years later, I'm still here talking about how to deal with the same topic. So I'm hoping that somebody listening can take it further than apparently I was able to. Next slide, please. So the abstract that I submitted had the basic idea that advances in information technology and use of scheduling systems have been very helpful in reducing cost, but not that helpful in improving the reliability or consistency of freight service. And my basic thesis here is that the structure of car scheduling or any system based on train connections is probably to blame, because train connections are not reliable, freight train connections. I understand probably in the Netherlands and England and various places I've been, the passenger train connections are indeed highly reliable, but not so for freight. Since the connections are not reliable, the trip plans are not reliable. And what that means, in my opinion, is that the trip plans are should not be service standards. You have to add a buffer. On the other hand, with PMAKE stands for probability of making connection. You can develop standards for yard performance, train performance that are related to standards for trip time and reliability, trip time distributions. So that's what we'll see today. Next. We'll go through 4 pieces here. First, we'll look at what service was like. I participated in probably the 3 major studies of service reliability in the United States back in the early 70s, the early 90s, and about 15 years ago. And I'll talk about the evolution of freight car scheduling. When I started as a grad student more than 50 years ago, railroads were just implementing terminal management information systems. And as soon as they were there, people started to think about freight car scheduling. So freight car scheduling started in the early 70s. I started thinking probabilistic analysis at the same time. And what I will show throughout this talk is that the PMAKE analysis provides a better way to predict service levels in structure operations. Next. So first, OD service levels. This is one of the freight yards out in North Platte, Union Pacific. Next. So let's see, what was service? Now it's interesting, back when the freight car utilization program began in 1975, that was a US government, Federal Railroad Administration program that involved the Association of American Railroads and several shippers, including General Mills. General Mills and a couple other companies provided full-time manpower to work on this research program, which lasted about 7 or 8 years, multiple phases. But at the beginning, one question was, well, how reliable is service? And the railroads didn't have the information because most service was interline. So General Mills provided some trip time distributions, and the average trip time was 6 days. They actually had a standard for each trip, 5.3 days, and they measured performance relative to standard. And on time or early was 61%, no more than 1 day late was 78%. What does that look like? That's the next slide. So this is one of those 24 trip times. It's not a very long trip, 217 miles. And this had a standard of 5 days. The average was a little bit longer. On time or early was 60%. No more than a day late was 80%. And I would submit that that is typical of general merchandise traffic in the United States and Canada back in the early 70s. And it's obviously not completely consistent, but you're trying to get on time plus or minus a day, and that's 80%. Okay, next slide, please. This shows the General Mills along with DuPont and Allied Chemical, which had similar experience. You know, the typical move was a week or so, and the average 2-day percent is like taking that distribution and taking the best 2 days and added it together. So that was like 50 or 60%. In some cases it was better, but that's where we're starting. Next. Let's fast forward now 35 years. One of the last projects I worked on when I retired was for the American Short Line and Regional Railroad Association. And there was a study of a bunch of moves that originated or terminated on short lines. And this is a typical example. This is an 8.5 day average. The standard deviation is close to 3 days, and it's a little bit less consistent than the one I showed earlier. And next slide. This shows that that particular movement was kind of typical for the whole set of 39 moves. Average time, something like 7 days a week, plus or minus 2 or 3 days. And 2006 was a time where traffic volume had boomed on the freight railroads, in large part because oil prices had boomed, and more traffic was moving by rail for a while. Next. So the conclusion at that time was that the service in the early 2000s was similar to what it had been throughout the previous decades. And service has been a problem for a long time and still a problem then. Next slide, please. So that was kind of the depiction of what is service actually. Now we'll talk about freight car schedule. How did this get started? Next. Southern Pacific was a leader in adoption of computer technology for management. And they had a terminal information system, terminal management, called TIMS. And that had standards for train connection performance, which were based upon cutoffs for the outbound train. It was almost always 12 hours. So if the train was departing at a given time, any car that was in the yard 12 hours before that was supposed to make the connection. And the daily, weekly, and monthly reports showed various levels of detail about average time, consistency, the percent making the proper connection, and the cost. And their goal was something like, 70 or 80% connection performance over a period of a week or a month. That was pretty good. The goal was not 100%. Next slide. Now, I've got a lot of quotes in here because I think they might be interesting to read for anybody that's working on car scheduling type systems or trying to predict trip times and reliability. So Southern Pacific had the ability in the early 1970s to develop trip plans, but they didn't do it. They chose not to. They were working on exception reports so they could find the cars that were late. And this is from the Missouri Pacific's Computerized Freight Scheduling System State-of-the-Art Survey, 1976, which is an interesting document. It includes, 2 or 3 page statements with a lot of exhibits about what each railroad was doing related to information systems for service planning, service design. So Southern Pacific had the ability in their IT department to do car scheduling, but as shown on the next slide, they chose not to do it. The operating officer said, you just can't tell them what cars should be on a train. You have to have something to help them manage what's going on in the yard. And I remember in the 80s, we referred to this after a meeting such as a RAS meeting or one of the other professional meetings. We'd sit there, and after 1 or 2 beers, you might complain about some CEO having service by fiat and without any consideration of how to do it, just say it shall be done. So SP in the early 70s said, no, we do not want to go with car schedule. Next. MOPAC and FRA did want to go forward. Gurdon Signs of Missouri Pacific, he was a leading advocate for freight car scheduling. He was one of the most highly respected information technology people in the railroads. MOPAC was a leader in developing information systems, and they were a leader for next 10 or 15 years after they were purchased by UP even in promoting real-time information. So I ran into Gurdon Signs when he was sort of at the peak of his powers, and I was just starting out as a professional transportation planner. And he was advocating freight car scheduling, and every time in a meeting when I would suggest that there were some limits, I would be slapped down and asked to revise my language in the report we were reviewing. Okay, next slide. So this was the vision from that Missouri Pacific report. Car scheduling systems implemented across the nation have the potential to bring assembly line efficiency to America's railroads. Think about that. Next slide. Assembly line efficiency, really? Now you have trains that are arriving plus or minus an hour, and that's a nice train. That's a good train. Trains are going 24, 30 hours across the country. Assembly line efficiency? Not really. Next slide. In their vision, they had examples of train performance. So again, let's look at this. Train performance. An example showed a train that had a standard deviation of 9 minutes. The studies I'd worked on showed that typical train standard deviations were an hour or 2. Train connection performance, an example showed Fort Worth, 91% proper connections. No examples of trip plan compliance reports. In fact, I couldn't even find a single one in my files. I'm sure I have some someplace. But compliance with original trip plans turns out to be very low, as you would expect, having seen those distributions I showed you. Next slide. Yeah, so 9 minutes, 91% proper connections. This is not, that report shows the most, and I know, as I'll show later on, that Fort Worth was the best yard where this type of analysis was done, and the standard deviation of 9 minutes is probably the best train they could find. Next slide. Back in the 70s, there was a freight car scheduling conference, and a number of distinguished people from both the rail industry, the government, and from railroad customers gave talks, and the talks are included in that report I cited. And Wilbur Smith, vice president of General Mills, was one of the leading advocates for cooperation between railroads and customers to improve service. And he basically said, you know, my boss is not going to go for this freight car scheduling stuff. We're not going to believe it. And how does he say it? We have seldom seen a railroad performance capability to support scheduled dock-to-dock transportation. And I just stuck in the distribution I showed earlier. That's what he was looking at. And the idea that you'd have one blue column there saying the trip plan is 6.2 days, and that's when you're going to get it. He knew that that was not possible. Next slide. During that conference, that same conference on freight car scheduling, Don Dingle was the man who was working on the specifications for the car scheduling system. So he gets a question. Hey, you know, we only have 90% reliability in making a connection at the yard. If you go through 3 or 4 or 5, you know, service is going to, you're not going to get that level of reliability. So if we could have something reliable enough for freight car scheduling to work, we wouldn't need freight car scheduling. Next question. So Don Dingle, well, the next screen is coming up, is thinking, how am I going to respond to this? And what he says is, well, you know, good service needs good plans, blah, blah, blah. Well, car scheduling will find problems. You know, we'll fix it. We'll fix it. Now, when I go back and read this after 35 years, I realize that both the questioner and the responder, Don Dingle, they both accept the fact, the idea, not a fact, the idea that the trip plan generates a standard. Next slide. Now, I've had 35 years to think about this, so perhaps I shouldn't be so self-righteous. But the answer is, if you've got an OT trip time distribution that looks like that, you're not going to promise 112 or 144 hours. You're going to, your marketing guy is going to say, that looks like, you know, maybe let's tell them 180 hours. And the customer says, that's terrible. We can get, you know, 6-day service, a little faster service from the competing railroad. So you say, okay, we'll call it 168 hours and we'll be able to do that most of the time. Next slide. So with that in mind, Dingle could have said, okay, yeah, the percentage of cars meeting the original plan, that's not going to work, but that's not what we're doing. We're trying to understand what the whole trip time distribution will be based upon connection performance. And we could figure out from a distribution that, okay, the trip time, let's call it X days or less, 90% of the time. Or as I said at the bottom, just add a buffer to the trip plan. Next slide. Now from the operating side, Tom Lamphere was the vice president of operations for the Burlington Northern Railroad. And by the way, he and Wilbur Smith were both on the steering committee for the freight car utilization program. So these people knew each other and had long discussions about these topics. He said that looking at statistics and computers and what's in the computer doesn't deal with the real problems. Maybe things go on in the terminal. You get too much traffic. There's a bad ordered car you got to dig out. There's not enough power. And then he said, if you try to impose a system, you're going to have standards that are too long. And what he says, cars can be taken out of the terminal count that will artificially improve the terminal's batting average. And I once talked to a terminal manager in St. Louis area who said, just tell me what you want. I can manipulate the numbers to give you whatever you want. Next slide. And unfortunately, Lamphere was correct. No, I put this in based on my memory from, say, is my memory right? That was 20 years ago I'm talking about. Right car, right train was one of the many acronyms that was developed for the chief railroad presidents and others to talk about how they were having a new plan to improve service. But to get a respectable batting average, so it's a respectable consistency, cutoffs grew from a reasonable 8 or 10 hours to 15 or 20. Now, this morning, as I was looking through various piles of stuff around my desk here, I came across a case study of Radnor Yard, a major hump yard on the CSX Railroad. And that yard had 21, there was an example, 21 train connections for one outbound train, and 13 of the 22 were greater than 20 hours. So that's exactly what Lanphier proposed. Next slide. So this is basically concluding that there is capability, but skepticism, and it could take a long time to implement car scheduling. Next slide. In 1981, a few years later, there was a final report from that same FRA study that concluded that at 7 Missouri Pacific class yards, things had improved. The greatest improvement was at Fort Worth, where compliance with the trip plan, the train connection standard, was about 20%. Next slide. But of the yards they looked at, the one they cited was the best one. Only one yard had connection reliability for the whole period that was near 90%. At North Little Rock, a major hump yard, they never got above 75%. Now, in actual fact, 75% compliance with train connections is not bad if the cutoffs are reasonable, but it sure makes it look very bad for car scheduling. Next. I've got a series of comments in here that I came across from my own notes to meetings on interline service management in 1991. At that time, the railroad still did not have measures of origin to destination performance for their interline shipments. The customers had it, the railroads didn't. But some of these comments, and these are from my written notes during the meeting, the official minutes of the meeting didn't have these rather blunt statements. So Mark Becker, Burlington Northern, we didn't get any consistency improvements. Conrail, customers are concerned with a lot of things. Where we're not coming forward is with notification of delays, which is a major feature of car scheduling. And he said the marketing people quote performance. They sell the service based upon past performance, including the disruptions caused by weekends. And then this guy, John Ladd from Union Pacific, says, I structure service to be 60 to 90%. I'll put in a buffer of 24 hours to cover the possibility of a misconnection. Very logical. Next. This is more of the same. So in 1991, there are comments that the main thing here is that this task force, these are the leading people on each railroad concerned with freight car scheduling and trip plans, and they were not all agreed about the need for it. The customer wants to know the schedule, but isn't concerned with minor variations. Next slide. And the trend continued. Next slide. September 23rd, 2020, I sat in on one of the, I guess it was the RAS presentation number 6 or something, I don't know. And Carl Van Dyke was speaking. Carl Van Dyke, I supervised his thesis, and he went on to fame and fortune with models of the type that we're discussing today. And a couple of years ago, he said average yard times are typically 24 hours. Right block right train connection performance is about 70%. So I assume that service and train connection performance is no better today than it was 2 years ago or 35 or 40 years ago. Next. I came across the term CTA, and I didn't recognize it yesterday when I went back through my notes. That was committed time of arrival. And in one of these discussions, it was very clear that the marketing people talked about service trying to meet the commitments you made, not trying to meet the trip plan. And then freight car scheduling clearly is trying to provide information for the day-to-day operations, not trying to produce trip times. And the ETA's estimated time of arrival, not the same as the CTA. Next slide. So let's go to PMAKE functions. I don't know if people have heard of this at all. I'll try to go just give a quick introduction. Next slide. And I've used some of the original graphs back when we had to draw them by hand to put into a report. This shows a simple PMAKE function, probability of making a connection. If there's too little time between the inbound and outbound departure, you don't make the connection. If there's plenty of time, you still might not make the connection because there's not room on the train and various other factors. But you have that typical S-shaped curve. If you're an operations researcher, you immediately start thinking about a logit function or some kind of interesting but complicated mathematical expression. Next. This chart from that same report in 1977, Southern Pacific's TIM system, the terminal performance management system, showed percentage of cars making their connection, and it also had the available yard time. So this chart, I simply plotted all those connections, and then I drew a line and said, it's not a calibrated PMAKE function. That's just suggesting a standard that SP could use for connection performance. So if your available yard time was less than 15 hours, the suggested standard would be somewhere between 0% and 95% or so. Next slide. I was going to put a logit function on this slide added to this, but I didn't have the time or interest to actually put all those Greek symbols in there. And what we concluded was a piecewise linear function would work fine, and you could have these three parameters. T50, which turns out to be sort of like the average processing time, and Pmax, the maximum percentage you're going to get because a lot of trains are full, so especially on peak days. Maybe your trains are full on Thursday and Friday and Saturday, and then you work off the backlog on Monday, Tuesday, and Wednesday. Next slide. So the question for trip planning is, well, what's the cutoff? In this green area, if the cutoff is really low, like 3 hours, you're going to have most of the connections will be missed. If it's way up there past T50 plus T90, then you're going to get up to Pmax, which could be as high as 95 or 97%. And somewhere in between could be reasonable. Next slide. That's just showing a different option of having like an 8 or 12 hour connection reliability. And that blue arrow is showing that the delay depends upon the frequency. Most freight trains would have a daily frequency, so that's like 24 hours. On some cases, it might be 12 hours, or there might be 2 or 3 possible trains with a shorter connection. Next slide. So what I just went through said, let's look at train connection performance and come up with these functions. And then one day we had a case study down in the Macon Yard, Southern Railway in Georgia. And I remember we're talking to the terminal superintendent, a guy named Bob Reed, who had been a grad student at MIT working on processing time distributions for his thesis. And the idea of a process PMAKE function came to me. And the idea here is illustrated by these distributions. This is from a student's thesis written. He was comparing a hump yard in New England to one in France. And so the first distribution shows the actual train arrival time minus the scheduled arrival time. So it's taking the variability in arrival time, calling that kind of a process. Because trains, some at East Deerfield, some would arrive 3 or 4 hours early or depart 3 or 4 hours late. The French yard was a much more disciplined operation. They were operating freight in conjunction with passengers, and they had a great incentive to be more reliable than the US railroad. Classification distribution, 3, 4, 5, 6 hours, but sometimes longer. Next slide. This shows the assembly time and the departure deviation and the total processing time. So these are figures measures that can be obtained from any freight yard. I mean, back when I first went there, the yard masters were doing this by paper and pencil on forms, and some railroads can do this or have done this on had it automated. So you take that bottom and the total processing time, and on the next slide, just show that as a cumulative processing time distribution. That looks like a PMAKE function. And the one for Wappie Yard is considerably better than the one for Deerfield. Next slide. So you could just linearize that and get your T50 and T90 that could be used to describe a PMAKE function. Next slide. These are just showing some of the PMAKE parameters that were done in a couple of yards. 3 studies. The first study was the Southern Railway in '72. That was when Southern was ranked one of the 5 best companies in the United States, not railroads, 5 best companies. And in fact, those PMAKE functions were the best I've ever seen as a group. They ran a lot of extra trains at that time, and they had pretty good service. The Boston and Maine case study had more typical trip times. And then the Santa Fe case study was a time when there was tremendous congestion because of the Russian wheat deal at a time when we were selling wheat to the Russians. And operation was chaotic. Next slide. So what do we do with PMAKE analysis, and how does that relate to trip time reliability? Next slide. The trip plan has an operation like this. You have the origin yard, and you say, well, we're supposed to leave on time. Then we go to a local yard, and we've got 15 hours until the next train departs. And if we miss it, it's a 24-hour delay. We'll call that 15 hours, and so on. We have a cutoff for each train, and we end up with a total time in the yard. If there's an 8-hour cutoff, you add up all the numbers in that 8-hour cutoff column, you get 84 hours in the yard. You add a little more slack time, 12-hour cutoff, and that time in yard B shifts from making that first connection in 10 hours to making the second one in 22 hours. If you're making this into a trip plan, you'd add the time for the trains. I'm assuming that's 36 hours. So if you go with 8-hour cutoffs, you get a faster, shorter trip plan than if you go with 12 hours. Next. With PMAKE analysis, what you can do is each yard, you say, well, okay, we can get the probability it makes the first, the second, or the third connection. So now you have a distribution of times. And in this case, the expected time, if it's based upon actual performance, or the standard time, if it's based upon the standards for train connections, is 96 hours. Next slide. And you can take all of those connection probabilities and follow car through 1 yard, 2 yards, 3 yards, 4 yards, and end up with a distribution for the trip time. So in this case, it's 96 hours in yards, 36 hours in trains. And the next slide suggests the problem that you have then. You know, what do you call it? What's the reliability? If the trip plan was 120 hours, well, you've got 26 reliability. If you say, what's the maximum 48-hour percent? That turns out to be 83%. Or you can say, well, let's say add a buffer and say, what's the percent with the expected time plus 24 hours? That's 97%. So again, it's emphasizing this point, the trip time, the trip plan does not have to be the service commitment. Next. So if you follow through all this, what you end up with a consistent process for coming up with trip time distributions. So if you have a process PMAKE function, you're relating train performance, yard, classification performance, train assembly performance, availability of power for outbound trains. All those things are related to the PMAKE function that relates to the connection probabilities, that relates to the trip time distributions. And then the trip time distribution can be used to determine standards for trip times and reliability. Next slide. And that's what we did with the service planning model. We used PMAKE functions to estimate the distributions. In Boston and Maine, it was the first case study with this model, and they hired one of my students, Mike Messner. Andrew Jennings was a grad student with me. He worked there as a person who monitored service, and they actually had a consistent set of standards for a couple of years. You know, in the early 80s, most of the major railroads in the US and Canada used the service planning model for some type of operations planning. Nobody went as far as Boston and Maine did, setting up the whole system, but they used it. And then Carl Van Dyke set up his own firm to work with the service planning model, and then became multi-rail and a lot of additional bells and whistles for setting up blocking and train schedules. Next slide. Algorithmic blocking, I mentioned that. I believe Roger Bauer has spoken to this group about Southern Railways, Norfolk Southern now, use of algorithmic blocking. A lot of these models are based upon cutoffs for train connections, and that works best for real-time control. But as I've been saying, if you're looking at what service do you promise the customer, you're looking at a longer time period. Next slide. So summary. Why doesn't car scheduling work? And I did want to mention one article. Chef Lang was a professor at MIT who called me up when I was coming out of the Army and asked me if I wanted to work on rail freight service reliability. And I thought I was going to college to study urban planning, but urban planning didn't offer any money. So I said to Chef Lang, yeah, fine, great, I'll work for you. I didn't know then that he had been the first Federal Railroad administrator, and then he went on to the AAR, Association of American Railroads, and was in charge of special planning studies. And he wrote an article about 15, 20 years ago, Freight car scheduling, what's the point? And his conclusion, after going through similar analysis to what I've gone through today, was you don't need freight car scheduling because, you know, the interest costs that were so high in the 70s and made inventory important aren't that important anymore, and the freight car scheduling doesn't work because the connections are unreliable, blah, blah. But he kind of, even then, accepted the notion that the trip plan equals a service commitment. So my only quarrel with him would be that the trip plan doesn't have to be the service commitment. And the freight car scheduling advocates who were promising assembly line efficiency had oversold what was possible. That led to a whole history of railroad presidents overselling what is possible and continual disappointment in performance, rather than having a continuing process for improving operations or using statistical process control to figure out what's going on in the terminal. I also mentioned that railroads operate 24/7 without a reservation system. The only person I know who was interested in reservations for freight or for certain classes of freight was Riley McCarran when he was CEO of Wisconsin Central. And he was probably one of my best graduate research assistants. He actually programmed the service planning model as his master's thesis, which is kind of a remarkable feat. And I'm sure a lot of people, certainly from the US, remember his passing with some sadness a few years back. Okay, where am I end up? Freight car scheduling provides excellent capabilities for answering queries about car location, but it doesn't provide a mean for developing service commitments. And we may have one or two more slides, one more. And the conclusions from the 70s are valid today. To deal with unreliability, you need to get into the yards. You need to understand how train reliability and the scheduling of switch engine crews and inspectors and the way you plan the use of the class tracks, all that relates to reliability. And the PMAKE analysis is an analytical device that allows these measures at different levels to be consistent. And I haven't mentioned operating service plan until this point, but the operating service plan idea says that service comes from the operations plan. You don't design the operating plan to meet the service plan. You have an operating plan. What is a service that will provide? And if that's not acceptable, then you have to go in and change the plan, which might include schedules, resources, contingency plans, control systems, the whole thing. And I reviewed Hunter Harrison's book on, I don't know if he called it precision railroading, but that was one of his terms. And that's the kind of thing that he was advocating. Final slide, I think, is just a color photo. Not quite in focus, possibly like my presentation, but you try to take 50 years and figure out what has happened over 50 years and try to condense it to a few slides. You have too much material to work with. Be happy to answer any questions, or also can provide a bibliography, and a lot of the papers that I've referenced are either available online or I have them in electronic form.
Yeah, okay. Well, thanks a lot, Carl. It was a really interesting presentation showing a pretty big time span and developments for the last 50 years. So we got quite a few questions so far. So
okay.
I would like to start with simple ones. It comes from Charles Butt, and his question is that you basically from the beginning started showing PDFs when talking about distributions. So his question is, what about using, well, sorry, you use CDFs, but so why using PDFs instead of CDFs?
Why am I using PVS instead of PBS? What?
Probability distribution function
Oh,
versus a cumulative distribution function.
Oh, okay. I showed examples of both of them. The PMAKE function is kind of related to the cumulative distribution of processing times multiplied by, reduced a little bit because of PMAX. The trip time distributions, I guess I showed those as trip time distributions because way back when I first saw them, that's the way General Mills and Allied Chemical and DuPont showed it, and that's how people talked about it on the railroads. So it's, you know, depending on if you're looking at the 90th percentile of the trip time distribution as the service standards, then obviously you're using a cumulative trip time distribution, but there's no special reason that I can think of.
Can I jump in slightly here? This is Carl Van Dyke. Also, keep in mind that you need a probability distribution function when you actually implement the use of a PMAKE function within an algorithm, because you're looking at each instance of a connection event independent of all other connection events. And for that, you need a PDF.
Yep.
Yeah, but the CDF and the PDF are the same thing. One's is showing it mathematically different. And if you look at the meta log distribution that I put in the chat from Tom Keelan, it will provide both if you just feed it the data that you have for that historical data. And it gives you, it'll tell you which one's the best. And it's not like a crystal ball that's giving you, setting it to known functions, a log normal or beta, or, you know, whatever you want to think about, exponential Poisson. So it's very different from what you've ever seen before. It's actually being described as a new distribution on the same level of a normal distribution, if you will. But it'll fit all of those distributions.
Great.
Okay, and staying in the same realm, you talked about linearizing the PMAKE function. And the question coming as well from Brian was, how would you introduce it in the scheduling model? So it seems that it would work for pure linear programming problems. So did you spend some time there, and how to use it in practice?
Okay, there's two situations where you might want to use a model. If you're a member of the railroad application section with a degree in operations research and you're doing the programming, you would probably be looking for the best functional form to use in whatever program you're developing. If you're in the situation I was, going out to a yard trying to explain to a yard master why what a PMAKE function means, and you go in there and start talking about something like a logic function, or you talk about, you think I was confused by a PDF and CDF, you'll get to the yard master and you say, what the hell are you talking about? But if you go in there and you're talking about average processing times and the variability in times, and I've got parameters that can relate to those. So T50 is actually average processing time. It was made it possible to communicate with the people actually doing the work, A, and then B, when we did case studies, and Carl Van Dyke is here, is one of the ones involved in the Santa Fe study, and you could develop a family of PMAKE functions, which you could do with the parameters for any functional form. But with the T50, T90, I had that chart that showed what the parameters were at various yards, it was obvious. I mean, once you understand what T50 and T90 are, you look at a chart and you see it's obvious which yards are good, which yards are bad, and how much they're different. If you put it in logit form or a non-linear form with various parameters that make it work right, it may not, well, the logit form, it would not be readily understandable to anybody coming from the railroad side, even if it is understandable to some of the people that are listening to me trying to explain this.
Okay, thanks. And I was wondering, so have you looked at the differences that, yep, in the data between the shaped curve and the linear approximation, how close they are in terms of hours or days?
At some level, it doesn't make any difference how close the calibrations are, because what you will end up using in the control system is a standard that you're trying to achieve. So in that chart I showed from the 1977, they had the Southern Pacific train connection data, and I just drew in a standard. That is the equivalent of saying the cutoff is 12 hours. So if you're trying to calibrate it and explain to your thesis supervisor that this actually does work, then you have to go through and show that the function you come up with, whether it's linear or non-linear, whatever it is, you have to show that it matches your data. But if you're using it as a standard, you presumably set the standard a little bit better than past performance, or maybe not quite as good as past performance if you're spending too much money achieving highly reliable service. And then you would monitor it over time to see whether you are getting close to standard or not.
Okay, I see. Thank you. And then jumping to a slightly different topic. So it was actually brought by Carl as well. So you gave a reference to Green Cargo in Sweden, and showing that they have high reliability, but also the system is significantly different. Their booking system guarantees capacity on the trains, tight schedules, and it has tightly run up yards as well as reliable equipment. There is much more on agreements between operator and the shipper. So I think it becomes clear that US is not operating that way. And according to some, may not be operating anywhere in the near future. So do you see any practical solutions to the issue in the US, and what could be used to improve the situation?
Back around 1995 or so, Carl Van Dyke and I worked with Wisconsin Central. Riley McCarran invited us out there to talk about a reservation system. And in the notes of the meetings we had, the possibility turned out to be as follows. There was no, as you say, you're not going to put in a reservation system for the entire railroad. You can't have guaranteed service for all moves. What you could have is for a portion of the traffic to have high priority, and then look within the terminals and not just say, these are the high priority connections, do it, but have a process where you could have move cars through a terminal so that they would make their connections and have a limited type reservation system where you could manage, at least provide the very good service for that segment of traffic. Now that was at the terminal level, and that would lead to improved connection reliability at the terminals. It wasn't trying to get to a, as I recall, not trying to get to a 100% reliable trip plan. But I would agree with Carl that the practical solution to this issue, the practical solution to reliability, I think, is accepting that this is more like kicking 50-yard field goals and extra points after the touchdown. It's more like extra point after a touchdown. Of course, you're trying to, or it's getting a goal in football in Europe as opposed to scoring on a penalty kick. You know, in one of them, you're supposed to do it almost all the time, and the other one, you know, you take your shots and you hope you get it once in a while. So I think the notion that Southern Pacific was using back in 1972 or 3 of, okay, here's our connection standards, and we're hoping to get 70% consistency on a, you know, week after week, month after month. And if we don't get that, something's wrong, and we have to find out what's wrong and fix it. I remember one railroad CEO talking about cutting costs, and it's hard to recall today perhaps, but up until about 2000, the railroads in North America had excess capacity. Capacity really wasn't a problem. And so there were generations of CEOs whose job was to cut, eliminate track, close yards, eliminate people. Instead of 600,000 or 700,000, you went down to 200,000 people, and the track structure declined. Cut. But the comment was, I figure you cut till you get to the bone, then you know you got a problem, then you ease off a little bit. And that attitude continued in the 2000s and later, when you really needed to be adding capacity and planning how to add capacity. The best discussion of that I've ever seen was a year after it was a major snowstorm that shut down rail operations in Chicago and probably a lot of other areas. But Chicago, the biggest freight terminal in the US, had just got really clogged because of snow. So the next year, the Chicago Terminal Management Group, I forget the exact name, but I know that Rich Gray, who has been a member of and given talks at RAS, was involved in that. And they had a winter operating plan where they went into detail about how they would have to plan on shorter trains. They would have to plan on having more crews, and they went into great detail about how they would handle that operation if they got another winter like that. So I don't, you know, he called, and Rich Gray used the term in another RASIC presentation, basic blocking and tackling, basic stick handling, they would say in Canada. I'm not sure what you would say in the Netherlands, but there's, you know, some sports metaphor that's probably appropriate, that it's getting down to the basics and having contingency plans, knowing that you've got weekly peaks in volume, that you've got bad weather, that you've got derailments once in a while, you've got things happen that you have to deal with. You have to have enough capacity and reserve to make it work.
Yeah, okay, thank you. Well, speaking of contingency planning, some people in this call are pretty busy with developing contingency plans for Dutch railways. So they're touching all important points. So yes. With this, I would like to end the presentation. And so I would like to thank Carl and everyone participating for great contributions. So this will be all for today. So I'll stop sharing, but also